So, welcome to the 8th week of the problem solving sessions of this course, Parameterized Algorithms. So, yeah, let's directly go to the whiteboard. Okay. So, today my plan is to first talk about kernelization. So, as you have suggested that I go through the idea of kernelization once, so I will recapitulate what kernelization is. Maybe we can take an example. And post that, okay, so there was one request from Shiva. So he wanted me to discuss the last video of 6th week, right? So I looked at the last video of 6th week. So I think this is from the chapter on tree width. So where they discuss the monadic second order logic on graphs and Courcelles theorem. So unfortunately, I'm not too familiar with these two topics, but definitely we will look at it. So I will go over it from the book once again, and then we can talk about it maybe sometime in the future, but not today. Okay. And then we'll look at one or two problems of week 8 questions. And before going through the questions, we have to look at some of the concepts. Okay. Okay. So without further ado, let's jump in. So just a second. That is the marker. Yeah. So we are familiar with the problem of vertex cover. So in the vertex cover problem, we are given a graph G, which has a vertex set V and an edge set E. And we are supposed to find a subset S of the vertices. So our goal is to output a subset S of the vertices such that for every edge in the graph, at least one of the endpoints is in S. So at least one of the endpoints is in S. So at least one of U and V is in S. So this is our goal. So and when we are optimizing, so we have two versions of the vertex cover problem. One is optimization version where we're asking that what is the minimum number of vertices that we must pick to cover all the edges. And the other one is the decision version. In the decision version, we are asking that does there exist a vertex cover in G of size at most k. So in the decision version, we have an additional input k, and we ask that does there exist a vertex cover in G of size at most k. Okay. So we know that the problem, both the decision problem and the optimization problem are NP complete, and therefore we cannot hope to get a polynomial time approximation. Sorry, polynomial time exact algorithm. So polynomial time algorithm is ruled out. So but we have seen that using the branching technique with the help of kernelization, there are fixed parameter tractable algorithms for vertex cover. But before going there, let's look at a simple 2 approximation for vertex cover. So in general, if somebody asks this question that, okay, does there exist? So the decision version. So somebody asks the decision version of the question, then what is the most natural brute force algorithm we can think of to decide if there exists vertex cover of size at most k? So let us say that n is the number of vertices in the graph and m is the number of edges in the graph. So how much time will it take? So first of all, what is a brute force algorithm to decide that in G whether there exists a vertex cover of size at most k or not?
So, so I can generate, say, some random binary strings whose length is equal to the number of the nodes of the given graph. So whenever I assign one, so it shows that yes, that vertex is the part of the vertex cover. And so once I identify that, yes, okay, these are the vertices which are the part of the vertex cover, then I can verify this thing in the, in fact, in the polynomial time, that whether indeed this is forming a vertex cover or not, in the effort of the order of n square. So, and in total, I can generate, say, so total number of the binary strings possible would be 2 raised to the power n, wherein the number of ones would be equals to, say, k, because it's a decision variant and the value of k is given to us, that does there exist a vertex cover of the size k or not. So the total running time would be of the order of 2 raised to the power n multiplied by n square.
Okay. So let's try to digest what you said. So you said that you will take a variable for every vertex and then you will consider a random permutation of these variables. And then each of these variables is either 0 or 1. If a variable is 1, then you are considering that vertex to be part of vertex cover. And thus, for every permutation of the n length string, you will be able to have a set of vertices which are presumably in the vertex cover, and then you will check whether this is indeed a vertex cover or not.
Yes.
Okay. Yeah, that is going to work. So basically, you are taking a subset of the vertices, and then you are checking whether this subset forms a vertex cover or not by simply going through every edge. And for every edge, you are asking that whether one of its endpoints is in the set of vertices that you have chosen. So yeah, so the running time, if you consider the running time, so if you also have, so in the decision version, we have an additional parameter k. So the running time in terms of k, n, and m will be, so you consider all the, so remember that there is no need to consider a set S whose cardinality is more than k. So we are only interested in vertex covers of size at most k. So we will make an assumption that okay, that we are only considering subsets. So S is a subset of V of the vertex set of size at most k, and there are n to the power k at most order n to the power k such subsets, and for each of these subsets you are deciding whether this is a vertex cover of or not. So the running time is at least order n to the power k. Okay.
Yes. Yes.
Yes. So
No, no, I do not agree with this. Yeah, see, this is n raised to the power k. How n raised to the power k? That we have been given, say, n number of the vertices, and are can we verify that whether it's a vertex cover or not in the polynomial time?
yes, so given a vertex, given a subset of the vertices, so let us
Yes,
say,
given the subset of the vertices, and in total there would be enormously large number of the subsets possible.
um, right.
So if a subset is given to us, then we can verify in the polynomial time that whether it's a vertex cover or not. But in total, we'll have to explore, say, 2 raised to the power n number of the possibilities. Depending upon the different subsets are possible. So if we are considering only the subsets of the length less than or equals to k, then how many subsets are possible whose cardinality is less than or equals to k then?
Right, right,
So
right. So the number of subsets whose cardinality is, let us say, 1 is n choose 1 plus the number of uh, subsets whose cardinality is 2 is n choose 2, like that. We have n choose k. Okay. So this is the total number of subsets of size at most k.
Yes. And this value comes out to be how much? Say 1 plus 1 raised to the power k. No, 1 plus 1 raised to the power. If we apply the binomial theorem here, say 1 plus x raised to the power n is equal to nc0 plus nc1 x plus nc2 x square, and we replace x by 1. So this is the expansion of 1 plus 1 raised to the power what? I mean, this sum should be equals to what?
So this would be, so how many terms are there? There are k terms.
Yes.
So let us recapitulate. So x plus y to the power n is summation k from 0 to n choose k, x to the power n minus k, y to the power k. Okay. So
Yes.
here we can take x to be 1 and y to be 1.
Mhm.
Okay. And the number of terms, n is k plus, right, n is k. So this turns out to be, this is correct, right? I'm just trying to, where is the problem? So here in the expression of binomial expression, the number of terms is 0 to n plus 1 terms are there. But here we have only k terms.
Yes. So therefore, this will be hmm, okay. So no issues because we can still consider this as replace x by 1 and then y by 1, and for all the values of the binomials wherein the value of k is greater, I mean, wherein the value of k is greater than this quantity n. No. Yes, yes. So for remaining values beyond k, the all the terms will become equals to 0. So if we go for this, so yeah, so nc1 and then nc2 and so on, we keep on expanding it and say till ncn, and somehow we'll have to stop till that level, till that k.
Hello, you're not audible. Hello, I think you have inadvertently muted yourself.
Yes. So
So yeah, so total number of subsets, if you don't have the subset size limitation, the total number of all subsets is 2 to the power n, I understand. But the total number of subsets where the subset size is at most k is how much? Is it order n to the power k? That is the question.
hmm, yes. So I think uh, maybe there someone might have formulated the result, or something else would be required. I mean, this result is not, uh, immediately known. I don't think that there might be some formula, but then
Yeah, so anyway, so this is still not polynomial time. Let us say that it is order n to the power k. So the largest term in this sequence is n choose k, and the
mhm,
largest term is order n to the power k. So there is no way that the sum is less than order n to the power k. The sum is definitely at least order n to the power k. That much we can say. And if k is not a constant, then
mhm,
so if k has dependence on n, so if let us say we say k is n to n by 100, something like that, then this is again not a polynomial. So in polynomial time, we're not able to. In fact, this is an exponential time algorithm if k is some order of n. So the brute force algorithm is going to take at least exponential time. So, but the good thing is, if you're insisting on, if you're not insisting on getting the minimum vertex cover. So if you are saying that, okay, I do not want you to output the minimum vertex cover, but if the vertex cover size is OPT, then you give me a vertex cover whose size is at most 2 OPT. So you have some tolerance for error. So if you have some tolerance for error, then there exists a very simple algorithm that outputs a vertex cover of size at most 2 OPT. So where OPT is the size of the minimum vertex cover. Okay. So suppose there is a graph, and in this graph there are n vertices and m edges, and the minimum vertex cover size is, let us say, 100. Then there is an algorithm that can give you a vertex cover whose size is at most 200.
Yes.
So this is similar to what you had initially suggested. So what you initially suggested is you are going to take one vertex for every, sorry, one variable for every vertex, and then you are going to consider a random permutation of these n variables, and then you are going to set every variable 0 or 1 depending on whether that the corresponding vertex to the variable is in the vertex cover or not. But here we are going to use a simple linear programming technique. So let me write it down formally. So for every vertex in the graph, consider a variable xv. So xv is a binary variable. So xv can take value. So xv lies in 0 or 1. So xv is 1 means that v is part of the vertex cover that we are willing to construct. And xv is 0 if v is not part of the vertex cover. V is not inside the vertex cover otherwise. Okay. So we have taken n variables for the n vertices. And now what do we want to do? We want to let us formulate the linear programming formulation. So we want to minimize. The objective is to minimize the sum of xv. So v is a vertex in the graphs. So we want to minimize the number of vertices in the vertex cover. So xv is 1 means the vertex v is in the vertex cover. So summation of xv is what? Summation of xv is nothing but the size of the vertex cover that we are willing to construct. So our objective is to minimize this summation, given that this is subject to that every edge is covered. That means out of the two endpoints of every edge, at least one of them is in the vertex cover that we are intending to construct. So for all edge u comma v in the graph, either xu or xv is taken. So if either xu or xv is inside our solution, if none of xu and xv are taken, then both of them are. So if none of, so consider this edge uv, this is part of the graph, and if this edge remains uncovered, that means none of u and v is in our vertex cover, then xu is 0 and xv is 0. So summation of xu plus xv will be 0. But if one of xu and xv is 1, one of this is 1, then the summation of xv plus xv is turning out to be at least 1. So this is the constant. So this constant is the vertex cover constant. Okay.
Yes.
And additionally, every vertex has a corresponding. So every variable is either 0 or 1. So every variable is binary. Okay. So this is the linear programming formulation. But unfortunately, because this is an integer linear program and integer linear programs are known to be NP complete, so we cannot solve this in polynomial time.
Okay.
So what we do, you know what we need to do in such a situation?
So can you slightly elaborate what this ILP stands for? And
Oh, it's integer linear program. So integer
Mhm.
linear program means you have a linear program like this. So you have a set of vertices, sorry, a set of variables. So in our case, the variables are corresponding to the vertices. And
Mhm.
there is an objective function in the vertices which we want to maximize or minimize. And there are constraints which are linear. That means there is no, so the power of each of these variable is 1. So that's why
Mhm.
it's a linear constraint. Such a program is called an integer linear program because of the fact that you are considering the domain from which the variables are to be assigned values to be integers.
Okay, no fractions allowed.
No. So what is the formulation? The formulation is you have a variable xv which
Mhm.
assumes the value 1 if it is part of your solution, and it assumes the value 0 if it is not in your solution. So there is
You
no 0.5 or 0.3 kind of
Yes,
assignments.
yes, that is well understood. So I was looking for the meaning of the term integer here. That how is this different from the linear programming thing, and only the integer linear programming.
Yes. So integer because the domain from which the variables are to be assigned values are integers. So in our case, there are two integers only in the domain. Maybe there are programs where you allow other integers to be in the domain. In fact, you can allow a set of natural numbers. But in our case, the formulation is such that you have 0 and 1 in the domain from which every variable has to be assigned values. So that is the
Yes.
reason we are saying that this is an integer linear program.
Okay, okay, okay. Yeah, clear.
Yes. So, and it is known that if you have a linear program where you are enforcing the constraint that every variable is an integer, then such a linear program cannot be solved in polynomial time and it is an NP-complete problem. So we are again in the same boat that we are trying to solve an NP-complete problem. We reformulated it in a different form and we have another problem which is again NP-complete. So we need to do some trick, and the trick here is to, this is a general trick and we call it the relaxation trick. So we relax the constraint and we say that okay, fractional values are also allowed. So instead of this, we will remove this constraint and we will say that okay, you can allow xb to take any value in the interval 0 to 1. So that means xb is allowed to take a variable value like this, a fractional value between 0 and 1. Okay. So if you allow this, then there are algorithms that can solve this linear program at most in cubic time. In order n cube time, wherein is the number of variables, it is possible to solve exactly this linear program such that this objective function is minimized. Okay.
Yes.
So we seem to have made some progress, but the progress is not very satisfactory because what is the meaning of a variable corresponding it to a vertex getting a fractional value like this, whether you include this variable, I mean vertex into the vertex cover or not. So there was
So
no clear distinction. Yes, go ahead.
So since now I have the solution with this fractional value, so I could have replaced this quantity by 1. So I would be getting slightly larger vertex cover, but then at least I would be having a solution in my head.
Okay. So you are saying that for every non-zero variables, you are going to take the corresponding vertex into the vertex cover.
Yes.
Okay. That is going to be a feasible vertex cover for sure. But the question is, how bad is the solution when compared to the optimal solution? So let us say the optimal solution is 100, so 100 vertices are sufficient. But because we are taking all the non-zero variable corresponding vertices, maybe we have ended up taking 1 million vertices. So maybe our solution is in fact far worse than the optimal solution.
Yes, because in this case, we could find a vertex cover there, but then we won't be able to quantify that how good or how bad, to what extent, I mean, how bad the solution is. Yes, that
Correct.
cannot be.
So this looks like we have made some progress, but we would ideally like to be uh, sufficiently closer to the optimal solution. And to do that, we will do another standard trick. So this standard trick is called uh, threshold rounding. So what we are going to do, so we are going to decide a threshold that if a given variable xv is more than the threshold, maybe more than equal to the threshold. So let us say the threshold is tau. So tau is some number between 0 and 1. Then we are going to include the corresponding vertex v into our vertex cover. And if otherwise else, so if the linear program says that xv has a value which is less than the threshold, then we are going to exclude this vertex from our vertex cover.
Yes.
So for example, if you set tau to be 0.5, that means, okay, all the variables whose corresponding values are 0.5 or more, you are going to take them. Then we can show that the solution that we have obtained is actually at most 2 OPT. And this is very surprising because it's a very simple algorithm. You just formulate the corresponding LP and you just look at the variable values, and it turns out that you just have to check whether a variable is 0.5 or more or not. If it is more than 0.5 or equal to 0.5, you take it into a vertex cover, and this is going to give you a feasible vertex cover. Okay, so why is that so? So in 2 lines, we can prove that this is a two approximation. Two approximation meaning that the solution is at most 2 times the optimal solution. The size of the solution is at most 2 times the size of the optimal solution. Okay, so first thing is consider an edge in the graph. Let us say u comma v, and you have the corresponding constraint that xu plus xv should be at least 1, and there is a solution. The solution respects the constraint, so that means that at least xu, 1 of xu or xv is greater than 0.5. So the minimum of xu and xv must be half or more. This is an implication, right?
Yes.
Yes, because the solution respects every constraints corresponding to every edge. Therefore, the sum of two variables is at least 1, means at least one of them. The minimum of this must be half. Is that true? No, so sorry. I wanted to say maximum.
It could be minimum also. I saw because minimum is greater than 1 by 2. Uh,
No, so
Max.
this can happen.
Okay. Okay.
So I wanted to say that at least one of these variables is half. So because our algorithm has set the threshold to be half, so we have definitely either picked u or v or maybe both. So maybe it is also possible that one side is 0.9, one side is 0.7. That is also possible. So in that case, we have taken both the variables. But anyways, for every edge, this is ensured that at least one of the endpoint is taken. So every edge is covered, that is ensured. All right. Fine. So what else? Now we want to argue that we have a two approximation. So what is the sum? So ours, so this is the objective function. So let me just copy the objective function. So consider this sum. Okay. So this is the LP sum. So this is the LP sum. So and OPT is the optimum vertex cover. So what is the relationship between OPT and LP sum? Not to OPT, I'll remove two. So OPT is the integer optimum, and this is the fractional optimum. So the question is whether this is greater than equal to or less than equal to.
Yes. So the this thing is OPT would be, so this sum would come out to be, so in the worst case scenario, what I mean, it is quite like here in this case, we are taking this value as 1.6, wherein the reality could either be uh, 1 or it could be 2. So say if it is the case of that only one vertex has to be included, but we have taken both, so therefore this LP sum would be greater than this OPT. However, there could be a scenario wherein the both the vertices have to be taken, and we have taken only this thing. Uh, but the constant, yes, we have taken only one out of these two. But we have taken one only when this is half thing. So half of this and then half of this. So I think that OPT would be greater than this thing.
No, so what is OPT? OPT is not the solution. So after rounding, let us do some more naming. So after we have applied this rule that for every vertex which has a value more than 0.5, you are taking
Mhm.
it. So let us say
Yeah.
the solution that we have output. So we are outputting a solution. Let us name it SOL sol. Okay. So
Mhm.
definitely this size of sol is more than the size of OPT, or at least the size of OPT. OPT is
Yeah.
what? OPT is the minimum vertex cover given the graph.
Yes. So
And
this solution, yeah.
go ahead.
Yeah, yes. So yes. So then the sum of this solution would be greater than this OPT.
So here, so you are saying that we should have this relationship.
Yes.
Correct. Is that correct? Probably. So right. See, let me rephrase what I wanted to say. Let's look at the linear programming formulation. Let us say we have this formulation. This is asking that you give me the minimum value of this objective function, given that I force you to respect these constraints and the other constraint that you can take 0 and 1 values. Okay. So this is the integer linear program, OPT. So this the best solution, the optimum solution corresponding to this linear program is called OPT. Okay.
Yes.
And now consider the relaxed linear program, this one. So here we are asking the question that you give me the minimum value of this objective function, but here your domain is much larger. I allow you to have the domain The interval 0 to 1, you can take any values between 0 and 1. So I give you the liberty to make things even better. So I give you the liberty to give me a smaller objective function value, because I'm not. So earlier your domain from which the variables have to be taken was only 0 and 1. Now you have a larger domain, 0, 1, and all real numbers between 0 and 1. So because you are minimizing over a larger domain, so maybe you will be able to minimize even further. So
Yes.
the LP sum that you will obtain is going to be smaller than OPT. So OPT is at least, because we're minimizing. So nobody can minimize beyond LP sum. Does that make
Right.
sense?
Yes, yes, makes sense. Fully makes sense.
Yes.
Uh, But the point here is that whatever we are getting, will this be a vertex cover clearly? Will this be a vertex cover?
After,
Uh,
you mean after we have done the thresholding?
yes.
Yes. So after we have rounded based on the threshold 0.5. So consider every edge. So
Hmm.
for every edge, we have respected this constraint that xu plus xv is at least 1. That is respected because we have solved the linear program. So because we have solved the linear program, we respected every constraint of the linear program. And because we are allowed to take fractional solutions, so no matter what the values of xu and xv is, it is not possible that both the values of xu and xv are strictly less than 0.5. Because if that is the case, then the summation of xu plus xv will be strictly less than 1.
Yes, yes, yes.
So therefore, at least one of them must be greater than equal to 0.5. So therefore, max of both of them will be at least half, I mean 0.5. Okay.
Right.
So for every edge, when you're looking at the fractional values assigned to the endpoints, one of them you will find that is at least greater than or equal to 0.5. And that one you are taking because you're thresholding at 0.5.
Right, right, right.
So there is no way we have an infeasible solution. Every edge is in fact covered.
Correct. Yes.
Okay. So now the feasibility of the solution is established that, okay, this is the trick. We have this technique of threshold rounding, and this in fact gives us a feasible vertex cover. But now we want to argue that what is the size of this vertex cover and how does the size of this vertex cover compare with the size of the minimum vertex cover.
Yes.
So now we have established this relationship that the fractional LP sum is smaller than OPT. Okay. Now consider the LP sum. So what is the LP sum? What is the objective function? The objective function is the sum of these variables. So how many variables we have? We have n variables corresponding to the n vertices. So some of these variables which were less than 0.5, we are not. So we are rounding them to 0. We are not taking them. So they are not contributing to our sol. So sol is after we have rounded. So some of the values have become 0. Some of the values have become 1, like that. So this is sol for us. So now we want to say that how big is sol with respect to OPT. Okay. So now,
But I have a query here.
yes.
That this OPT cannot be considered as the minimum set of the vertex cover. At the most, it can be considered as the optimal solution of the ILP problem, which
Yes.
is so at the so this OPT is not the vertex cover. It is the optimal solution of the ILP problem because we cannot find something which is smaller than the optimal value. Otherwise, how can we say that this is the optimal value? So if OPT is the ideal case of the solution of the ILP problem, then this LP sum is the approximate case probably. Is this is this is this true?
No, so you are saying that the minimum vertex cover size is not
Yes.
OPT.
So minimum vertex cover size is not OPT. Uh, so minimum vertex cover size is OPT. Yes, this is correct. But
No, no,
how can I?
OPT is the optimal solution of the ILP,
Yes,
and
and
it is, and then you are saying that the optimal solution of the ILP is not the minimum vertex cover size.
yes, because the thing is that if OPT indeed is an optimal solution, how can this be greater than something? Optimal itself means that I mean
Yes,
now,
yes, yes.
yes, now we can find something better than this.
No, no, the LP sum is maybe the LP sum is strictly smaller than OPT, but the LP sum is only the minimum fractional value corresponding to this uh, relaxed LP. So this is a relaxed linear program, and this is not representing exactly the minimum vertex cover problem. The exact representation of the minimum vertex cover problem is the integer linear program. Whereas the relaxed linear program is a structure that uh, we have formulated for our keys of arguments.
Mhm.
Okay, so it is very much possible that the relaxed linear program has a value which is fractional. Let us say that there are 100 vertices. I'm just saying, I'm just making up some numbers. So let us say n is equal to 100,
Mhm.
and this relaxed linear program has given some fractional values to each of these uh, n variables, and it turns out that the sum of these x1, x2 up to xn turns out is 37.325. That is like perfectly possible. Whereas for the exact representation of the integer linear of the minimum set cover problem,
Mhm.
that number has to be some integer. So let us say 45. So it means that there are 45 vertices which you must pick in your vertex cover such that all the edges are covered.
Yes. So at the most, I can. So at the most, I agree that yes, this OPT is greater than this LP sum. But then, which vertex cover shall correspond to this sum? Which vertex cover shall correspond to this LP sum would be decided by us, depending upon this threshold or other parameters. That once we found the sum as 37.325, then corresponding to this sum, which all vertices would be there, which can be viewed as the vertex cover.
So you are saying that there is actually a vertex cover of size 37.325 or maybe 38.
No, no, no. So there is a vertex cover. There would be a vertex cover. There could be a vertex cover, not would be,
Yes,
there could be a vertex cover wherein the sum of the values assigned to all the vertices is equal to 37.325. There would be a subset of the vertices whose sum of the values assigned is equal to this quantity. But then out of those subset of the vertices, which vertices indeed will become the part of the vertex cover would be decided by us.
correct, correct, correct. That is true. That is true. That is right. So once we decide that okay, these are the vertices which we are going to include in our vertex cover, then that number may rise much higher than 37.325. In fact, it can become as large as 45. That's what I'm saying. So that
Okay.
number may be much higher than 37.325. It need not be the ceiling of 37.325. It could be higher.
Okay.
Okay. Right. But the thing is, if we have done the thresholding in this way, that for all vertices whose corresponding uh, variable value is 0.5 or more, then if LP sum is this, then the vertices that we have taken will be at most 2 times this thing. So what is 2 times this thing? In this case, 37, 37, 74, 75. So we won't be any poorer than 75. That's what we are going to argue now. That the way we have done the rounding was clever enough so that we did not go too far from the LP sum. We did not take too many vertices as compared to the LP sum. That's what we are going to argue now.
Okay.
So yeah, so what I was saying, okay, so this is the set of variables, and the sum of these variables is our objective function. And whenever we have seen a value which is less than 0.5, we discarded it. And whenever we have seen a variable with value more than 0.5, we have rounded it up and we have made it 1. So that's how we have got some variables set to 0 and some variables set to 1. And the variables which are set to 1, the corresponding vertices we have taken in the vertex cover, and we have established that the vertex cover we have obtained this way is indeed a feasible vertex cover. Okay. So now what is the sum that we will get? So observe that the, okay, let me give it a thought. So you have gotten rid of the smaller values. Okay, just a second. So consider the objective function summation xv. V belongs to the vertex set. So right. So this is the objective function. So let us divide the objective function into 2 parts. So those vertices for which, so V such that xv is strictly less than 5, summation of these variables plus those vertices such that xv is at least 0.5. Okay. So this part you are immediately ignoring. So you are saying all these variables whose value is less than 0.5, you are setting it to 0. And this part for every variable, you are setting them to 1. Okay. So we can say that this is less than equal to, 2 times summation xv, v such that xv is greater than equal to 0.5. Okay. Why can we say that? So consider a value here. So a variable xv, let us say it is 0.5. So 0.5 you have upgraded it to 1. 0.55 you have upgraded it to 1. So every variable you have upgraded to at most twice its value. Okay. So XV is replaced by at most 2XV, correct?
So what if that we have values like say 0 point many vertices having
Okay.
the value say 0.4,
So those things
and
are ignored. Those things are
so
set to
so
zero.
yes, yes, so that will be the loss of how many values? Loss of many values. I
Yes,
mean,
yes.
if it's fine, and then we have very few vertices of the value say 0.85. So if I convert 0.85 into the 1, then I got the profit of 0.15. But if I lost many vertices of the value 0.4, then there
What
is
do you
a
mean by
clear loss.
profit?
So profit here is that so I mean whatever conversion we are carrying out here is ultimately this value is coming from this LP something.
Yes.
So yes, so then the value of this thing, this solution would be could be much smaller than the value of the LP sum.
Yes.
So
So
if
is that
this
a
value is, yeah, please.
so what is a profitable situation for you? To get more LP sum or less LP sum?
So profitable situation would be for me is that I got
Minimize, you want to minimize things.
yes, I want to minimize the thing. So
So
seems it
you
would be that I have lesser value of LP sum.
yes. So whatever LP sum you had, you
Yes,
are whenever let us say there is something which is 0.499 and then you are setting it to zero, that means you are gaining, you are not losing because you want to minimize.
yes,
If
yes.
you have 0.51, you are setting it to 1, that means you are losing because
I'm
you
gaining.
don't.
I'm gaining because 0.51 has been converted into a 1.
So what is the so if okay, say if you have a maximization problem and
Yes,
if you are increasing the values of the variables, then you are gaining. But we have a minimization problem. So we want to
yes,
minimize something. So the something is a sum of variables. And these variables, we are saying that we will set them to 0 or 1. Now, whenever we are setting something which is very close to zero point 0.5 to 1, so we are actually increasing the total sum, which we do not want. We want to have the sum to be as small as possible.
mm-hmm,
So
mm-hmm.
since we are minimizing, so whenever something like zero point 0.4, we are setting it to 0, we are gaining because the total sum is reducing uh, because of a rounding.
Yes, yes, true. And in this inequality, I fail to observe that you have only considered those vertices in the right hand side whose value is greater than or equals to 0.5. So I made this argument by assuming that as if in the right hand side, towards the right hand side of the inequality, we are considering all the vertices uh, of the given graph with all the values. But then here also we are considering only those vertices whose value is greater than or equals to 0.5. So this is, I mean, there is no issue because this left hand side clearly would be less than or equals to the twice of this thing because
Yes,
because this one term has been converted into zero.
correct. So you are convinced about the correctness of this inequality.
Yes, yes, yes.
Yes. Now I did all these things, but it was not necessary to do all these things. So now what we will do? Okay, so this inequality is established. So we have something which is larger on the right hand side. We have something which is less than equal to on the left hand side. Now, if we add some positive quantity on the right hand side, that will still hold. So we can now add 2 times all these vertices such that xv is less than 0.5. That is also true.
Yes.
So this is nothing but 2 times we are taking 2 common. Then this is nothing but uh, so this x is so 2 times the sum of the variables in the fractional. So 2 times. all the
LPC.
fractional sums. Yes. So I have to actually change the, we'll say x dash. So let us say that after rounding x, so all the x, so xv is the fractional solution we have obtained by applying the linear program solver. And once we have rounded, we have x dash v, which is 0 or 1. So this is rounding. So we're actually willing to find that what is the rounding, what is the sum after the rounding. So our solution size is nothing but the summation of the variables after the rounding is done. So this is, yes. And just a second, let me verify if I'm saying the correct thing. I want to say that this thing is OPT. I've actually proved that sol is at most 2 times OPT. But let me just verify if this step is correct or not. Yes, yes. So we'll just say x dash. Okay. Now these things we can just, okay, this will keep this. So basically we are keeping this. Let me reiterate over the once again go over the argument. Okay, so we want to find a relationship between the solution we have obtained, the size of the solution we have obtained, with the size of the optimal solution, that is the minimum vertex cover. So linear program solver has given us some fractional values for every vertex p. We rounded these values using the threshold rounding. So after the rounding, we have for every x dash v, xv, we have x dash v. So this is 0 or 1. So now for all the vertices, we take the sum of the x dash v's. So this is nothing but the size of the solution that our algorithm is providing. Okay. Now we partition this summation into two parts. In one part, we are considering those variables for which the original fractional solution assigned by the LP solver was less than 0.5. And those variables is on the other side, on the other sum, we have those variables for which the LP solver assigned value more than 0.5 or less greater than equal to 0.5. Now this part is remaining as it is, and this part we are upper bounding by 2 times xv, and that we can do because x dash v is at most 2 times xv for every vertex which is 0.5 or more, and that is why this inequality holds true. Now if you take 2 common, then this summation of uh, okay, so one more thing. Okay, we have I don't know, am I making some mistake here? Oh, this, okay, remember. Okay, one more thing. So this x dash v is nothing but 0, right? So for all xv which is less than 0.5, x dash v is 0. So this part is 0. So we can also upper bound 0 by something like 0.1 or 0.2, that is xv. So now on the right hand side we have only xv's, sum of xv's. On the left hand side we have sum of x dash v's. The sum of xv's taken over all the vertices is nothing but the LPOPT. This is nothing but the LPOPT, and we have already argued. Where is this? Uh, so this is nothing but LP sum, and we already seen that LP sum is the minimum, so this is less than or equal to 2 OPT. So this we have already seen here, that LP sum is upper bounded by OPT. So basically, it was a simple argument, but maybe I made it a bit complicated while explaining. But I can go over it once again if you are not comfortable
In
with
this,
any of the.
no, it is understandable. Yeah. Yes. So I could understand. Yes.
Okay.
Yes, this is understandable.
All right. Okay. So what I managed to show is that this threshold rounding will give you a vertex cover whose size is not too far. In fact, it is within 2 factor of the optimal solution. Okay. So now we can take a break, and after 5 minutes we'll resume, and then we can see. In fact, my plan was to give you another simple 2 approximation, but in the interest of time, we'll see the kernelization based argument for fixed parameter tractability of vertex cover after this. Then we'll go to the questions.
Sure, sure, sure.
Thank you. Be back in 5 minutes. So Shivang is asking what is a series parallel graph and what can we say about its tree width? So I don't know the answer, but I'll just ask Google. Series parallel graph. Okay, so in graph theory, series parallel graphs are graphs with two distinguished vertices called terminals, formed recursively by two simple composition operations. They can be used to model series and parallel electric circuits. Let's look at some images. Okay, this looks like this resistor formations in electric circuits in parallel and series. So in what context have you come across this graph, Shiva? Let's look for tree width of series parallel graphs. So it says that it is well known that a graph is so it looks like that these, I'm not sure, I'm just doing a quick Google search and it says that it is well known that a graph like this is K4 minor tree or equivalently it has tree width at most 2. If and only if its two connected components are series parallel. Okay, this is one of the questions in the assignment. Okay, by policy, I should not be discussing assignment questions before the deadline. But my suggestion is it is it's not the exact question. All right. So I just looked up from Google and it looks like that these are graphs which are well characterized. And if we yeah, if we do some searching, we'll be able to get more information about it. So for the in the interest of time, I'll probably look at the question that is in the assignment, and if it has no conflicts with what you are asking, then I can revert back to you. Is that fine? Okay. So let's get back to our discussion.
Yes, so is this written in reverse? Because in the right hand side of this inequality, the right hand side is the LP sum, because here we have XBs and then XBs everywhere. And in the left hand side, since we have the modified XBs, so wouldn't be the optimal value or something else? But certainly
So
the right hand side refers to the LP sum, the twice of the LP sum.
this is LP sum, right?
Yes.
So we have already established here that LP sum is the smallest, uh, you know, because we're optimizing over a larger domain of 0 to 1. So the minimum LP sum, so the minimum objective function value that we can get is LP sum. So OPT, because OPT is optimizing over only the domain of 0 and 1, is more than equal to LP sum. So this part is okay.
So I'm referring to this inequality. In this inequality in the right hand side, since we have XBs here, so shouldn't be the LP sum. Yeah, this quantity is the LP sum, the twice of the LP sum, isn't it?
Yes, yes,
Oh,
that
I
is
see. Yes, now I understood. Since the entire right hand side is the twice of the LP sum, so that would be less than or equals to the twice of the OPT. Yes, I got
okay.
this interpretation correct. Yeah, right.
All right.
Yeah.
So yeah, so what is covered is NP complete, but we have a two approximation and it is simple. It is as simple as solving the LP and taking threshold rounding. But it turns out that there is It's very simple kernelization technique, which can give not a polynomial time solution for the vertex cover, which is not possible anyway, unless P is equal to NP, but which can give a faster uh, algorithm for vertex cover. So initially, when we started with, we said that the brute force algorithm for vertex cover is at least going to take order n to the power k time for the decision version of the vertex cover, that whether there exists a vertex cover of G of size at most k, we cannot help but incur a running time of order n to the power k if we are simply using the brute force algorithm. But now let's look at in the context of kernelization how vertex cover can be tackled. Okay, so let's first understand what is kernelization. So kernelization or a kernel is an algorithm. Okay, this is an algorithm. Yes. So this takes as input some instance of the problem. So an instance is denoted by I comma k. So in the vertex cover setting, I would be the graph, G, and k is the parameter. So that is like asking that uh, whether there exists a vertex cover of size at most k. So this is the parameter of the uh, instance. I mean, because we are in the domain of uh, parameterized algorithms, we always have fixed parameter tractability with respect to some parameter. In this case, the parameter is the output size, like whether the output size is at most k or not. Okay, so what does the kernel or kernelization algorithm do? It takes an instance, in this case a graph and an integer k, a positive integer k, and it produces an equivalent instance I dash comma k dash. So this is an equivalent instance. So this is original instance, and this is an equivalent instance. Okay. So what is the characteristic of this equivalent instance? So this equivalent instance is a reduced instance in the sense that the size of the equivalent instance plus k dash is bounded by some function of k. So g is some function that we can compute that goes from the set of natural numbers to the set of natural numbers. Okay. So remember that what was the input size? So you knew that the vertex set had size n, the edge set has size m. But now after the reduction, so kernelization is nothing but some reduction into an equivalent instance, where interestingly the input is bounded by some function of k and has no dependence on n and m. That is the beauty of the kernelization. So you have got a smaller instance, and on this smaller instance, you can probably do something brute force and get a comparatively smaller running time than the running time of the brute force algorithm on the original instance. Okay. So this is the
So,
high level. Yes.
so what could be the, I mean, a slightly simple intuition of uh, using kernel, like say in machine learning, we have been using kernel to project anything over the higher dimension. And if I view this kernel also from the same perspective, then how are we carrying out the transformation, the transformation of the original instance of the problem along with the given parameter into something wherein the size is the sum of the sizes of everything is just a function of only one parameter. So I mean,
So if you want to view kernelization from the perspective of uh, machine learning, convolutional neural networks, and other things, then I do not know whether there is a direct correspondence to.
no, I'm just focusing on the resemblance in the name. That there also the name is kernel only, and here also the name is the kernel. So probably there could be, and moreover we are carrying out some kind of the transformation here also. So probably there could be some similarity, because here if we transform an instance of the problem into some other instance of the vertex cover along with some other parameter. So, and by the way, why can't we eliminate this k dash from here and we simply write that I dash is less than or equals to say gk, if this k dash can be somehow submerged or can be included in this gk thing, then it
Yeah,
then
so if
then it will make sense. I mean, uh, more sense.
so, yeah, I mean, whichever is the dominating term, I don't know if k dash dominates I dash. So if k dash is much larger than I dash, then we probably cannot simply write I dash is less than equal to gk suffices.
But in
So
any case, this k dash is going to be smaller than I dash because I mean, the question is that does there exist a vertex cover of the size less than or equals to this, and which would definitely be less than the number of the vertices of the given graph.
no, the
So there,
definition of kernelization is generic. It is not with respect to vertex cover problem. So conventionally, for the generic definition, they are writing it this way, that the reduced problem is such that the parameter size plus the instance size is bounded by some function. That is by convention they have written. Of course, what you are saying is correct. For vertex cover, k dash is at most I dash, because k dash in this case the parameter is the output size, and the output size is at most the input size, and it makes sense to remove k dash for vertex cover. But otherwise, in the general
so
definition, this is the case.
yes. So if I consider the value of k is equal to say 10, and a problem instance I is given, my question is that does there exist a vertex cover of the size 10? And I use this kernel thing here. So this which will transform my problem into some other problem, and will give another some parameter, and its sum would be less than or equals to the function of 10. How does this make sense to? I mean, this intuition is bit. I mean, it's not
Okay.
easy to comprehend. Yes.
So you are saying that y is the function on the right hand side, the function is on k. So the function is dependent only on k. Why is that so? That's what you're asking?
So my question is that why are we giving so much importance to this k thing here? So why can't we? I mean, can we have
So k
something?
is our parameter. So we want to design a fixed parameter tractable algorithm, which is of this sort, which runs in 2 to the k times n to the constant time. So this is a polynomial time algorithm if k is constant. Okay.
Oh yes. So it means that we want to, since we want to decide that does there exist a fixed point tractability or not for this particular problem. So yeah, so therefore we are modifying this problem in such a way. Yes, now it is understood. Yeah. Yeah.
Yes. So we are always interested in trying to see if we can have a running time which is of the form n polynomial in n but exponential in k, where k is our parameter. And if the parameter is within our control, then we will say that we have a polynomial time algorithm. In fact, see, n to the power k is also polynomial, but 2 to the power k is a better polynomial, I mean, smaller polynomial than n to the power k. So that's why you are saying 2 to the power k. We are insisting on 2 to the power k.
Yes, yes.
So to answer your question that why we using the word kernel and how does it relate to the use of the word kernel in other domains of computer science, and what is the resemblance? So I honestly do not know if there is any resemblance. So if you can tell me a few words on the usage of the word kernel that you have come across in machine learning, then probably I
Yes,
can
yes,
try to relate.
yes, 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 yes. So in kernel there, what happens that so I heard this term while using SVM, support vector machine. So there we use kernel to project the lower dimension data into the higher dimension data, so that the data becomes separable. Data becomes, I mean, linearly separable kind of a thing.
Okay.
So yeah, so that was the use of the kernel there,
So
and
kernel is a matrix for you, and you are using this matrix on another matrix, and you're taking some operation, and then the original input is going into another dimension.
yes, yes.
Okay.
in higher dimensions.
Yes.
Yes.
So I would say that in this case there is uh this is not, so this is okay. So this is only a set of reduction rules, and it is also a transformation, that is true, but it is not a matrix, it is nothing of that sort. It is just a set of reduction rules which will give you a transformed instance, and preferably a smaller instance than the original instance.
So there the kernel is not a matrix, but then it used to be a function, like say a mapping from say U2 to U7 or U4 or U3 kind of a thing. So
Okay,
there also it was a function, like say there could be various kernels, so it could be a Gaussian kernel or some other kind of the kernels.
all right, all right. Okay, so
Yes.
maybe I have to look it up, then I can answer you when I'm more informed about it.
Yeah,
Uh,
sure, sure, sure. I was just trying to understand this mechanism so that if I can relate the things, I would be able to remember this thing.
yes, yes, yes,
Yeah.
yes. But as we'll see an example now, that we'll see a small kernel for a simple kernel for vertex cover, then probably you will be in a position to compare the two things by your own, on your own.
Sure, sure. Yeah.
Okay, so let's look at a small simple kernel for vertex cover. Okay, so it's nothing but, as I said, is a set of reduction rules. So you apply the reduction rules on the problem instance. So the first thing is, let me just write it this way. So reduction rule 1, RR1. So you have an instance GK. So this is the original instance. So GK is, so here our IK is nothing but a graph G and parameter K. And we are asking the question that does there exist a vertex cover of size at most K in this graph? So the first thing is we apply the following transformation to the graph. If the graph contains an isolated vertex V, then what shall we do? Because it's an isolated vertex, we can be sure that there is no way we can include this vertex in our vertex cover if we want to minimize the vertex cover. So in the minimum vertex cover, a vertex that does not cover any edge cannot appear. So then we delete this vertex V from the graph altogether. And then we have the reduced instance. So we output the reduced instance. So that is I dash K dash for us, which is nothing but this vertex is deleted. And then again, you're asking that does there exist a vertex cover of size K or not, at most K or not. So this is a set of, so on the application of this rule on your graph, you got rid of some vertices. So now let's look at a more interesting rule. So it says that if you have a vertex, if there is a exists, if there exists a vertex V in the graph of degree K plus 1 or more, then what shall we do? So there is a vertex V that has too many vertices neighbors, and you're asking the question that whether there exists a vertex cover of size K or not.
So does there exist a vertex cover of the size K? Uh, Means I'm looking for that there should be K number of the vertices in the vertex cover. So if there is a vertex of its degree is greater than or equals to K plus 1, then it is uh,
Then,
yeah.
then what
So
can we say about V? Whether we should include it in the vertex cover or we should delete it from the vertex cover? I mean, is there
so
anything we can say?
so all the vertices whose degree is higher clearly should become the part of the vertex cover. Why? Because they would be covering many edges. But I do not find any relevance of having this degree as K plus 1 here.
Okay, so we look at it. What is the relevance of this number K plus 1? Then take V into the vertex cover and output the reduced instance, which is I dash k dash. In this case, this is you removed b, and you are asking that okay, one vertex is already gone, so now you are allowed to only take k minus 1 vertices. So if you answer the question that whether there exists a vertex cover of size at most k minus 1 in the graph g minus b, then you have essentially answered the question that whether there exists a vertex cover of size at most k in the original graph. So now to coming to your question that why is it k plus 1? So if you have any number which is smaller than k plus 1, let us say k, then you cannot be sure that okay, we must take v into our solution, because if you do not take v, then to cover all the edges which are incident to v, you have to take the neighbors of v. Now you are allowed to take the neighbors of all the neighbors of v if there are k vertices, because you're only asking the question that whether there exists a vertex cover of size at most k. But whereas if there are k plus 1 or more neighbors of a vertex, and then you are forced to take all the neighbors if you do not take v, then you will definitely violate the condition that the vertex cover size should not exceed k. So therefore the condition is implemented to make sure that we do include all the vertices of size, sorry, we do include all the vertices of degree k plus 1 or more. Otherwise we will not be able to satisfy this condition.
Why so?
Okay, so what is the condition? The condition is you want to output a vertex cover of size at most k.
Size at most k, and it means that there would be maximum k number of the vertices in the vertex cover.
Yes. So you want
Yes.
to output a vertex cover of size at most k. There should be at most k vertices in the vertex cover. And I am formulating a rule that you reduce this graph into a smaller graph. And I am formulating a rule that if you come across a vertex whose degree is large enough, so large which is greater than k plus 1 or so, then you are going to take that vertex into your uh, vertex cover. And why so? Because if you do not take v, then to cover all the edges which are incident to v, you have to take all the neighbors of v. And how many neighbors you have to take? At least k plus 1, because at least k plus 1 neighbors are there. And then you will be failing to satisfy this condition that your vertex cover size is k or less.
So my point here is that all these vertices ranging is starting from 1 and say till k plus 1 are further connected to another vertex, say v dash. So instead of taking the vertex v whose degree is say k plus 1, now I am taking including say v dash.
Okay.
And so if it is a problem of having say the multiple edges within the same vertices, that could be one issue. Or the other issue could be that even if it is not the directed path, then yeah.
No, no, so the graph is undirected.
So can we have the multi graph in which there are multiple edges in between the two vertices? So
No,
not the
you mean
multiple,
parallel edges.
not the multiple. Yeah, all these are parallels because we have the vertices ranging from 1 to k plus 1 here. Yes. So now instead of v, I have liberty to select say v dash.
Yes, that you can do. The point is you have a vertex v, then okay, so even if you take v dash, who covers this edge between 1 and v?
So yeah, yes, true. Yeah,
Your
yeah. Right.
your
So yeah, right,
your
right.
point is valid, V dash has
Yes.
to be taken, but V dash is responsible for covering the edges incident to it, but it is not responsible for covering the other edges.
Right. Right. Yes. Yes. So this vertex whose degree is greater than or equals to k plus 1 has to be taken. But apart from this vertex v, there would be other vertices as well.
Yes,
So therefore, in the right hand side, you wrote this value as k minus 1. Yeah, true. It's
yes,
correct.
yes, yes, yes. So now we are done. So given a graph, so now we have now consider this algorithm for finding vertex covered. This algorithm uses kernelization. I would so kernelization I would prefer to call it a set of reduction rules. So it takes an input graph. It scans for those vertices which are isolated. It removes those isolated vertices, and it also scans for those vertices which are high degree vertices. It picks those high degree vertices where high is defined by this having degree at least k plus 1, and then you are left with a reduced graph. Okay, and on this reduced graph you observe some properties, and then you do some further processing to get a vertex cover. So now let us observe some properties on this graph which we have obtained after applying the reduction rules. So the lemma is the following.
And these rules can be applied any number of the times.
This has to be applied exhaustively as so you will have to reduce the graph as long as it is possible to reduce it. You have to keep reducing it. So if you even if you have uh, one vertex left which is having degree k plus 1 or more, then you apply the rule. So you apply the rule exhaustively and you keep on applying as long as it is possible.
Okay.
Okay, after you are done, after you realize that okay, no further reduction of the graph is possible, then you make some observations. So the lemma says that if in the first place the instance that you had, so the instance that you had was ik, the ik was nothing but gk. If it was possible to obtain a size k or less vertex cover of this graph, that means if the instance was an yes instance, sorry, a yes instance. So if the instance admits a vertex cover of size less than equal to k, and you applied all the okay, let's do one thing. If let us slightly make it simpler. So if you applied all the reduction rules and you obtained the reduced graph I dash k dash, which is g dash k dash. So g dash is nothing but what is the residual graph after you applied all the rules exhaustively, the rule 1 and rule 2 exhaustively. Then you if the so this is an equivalent instance. So if the original instance the q is a yes instance, then this reduced instance is also yes instance. Okay. So if this is an yes instance, then the number of vertices in this graph will be bounded by some function of k, and it is precisely at most k square plus k. And the number of edges in this reduced graph is also bounded by a function of k, which is k square. And that is the beauty of the kernelization, that you got rid of n and m. Okay. Okay.
Yes.
I will prove this, but before that, what is it we have gained by doing the reduction?
So yes. So yeah, we could find the subset of the vertices. We need to pay more attention, and the I mean, we could reduce the number of the vertices and the number of the edges.
Yes. So now, if you apply that brute force algorithm, which we talked in the beginning, so we talked about this brute force algorithm in the beginning, and we said that because there are n vertices, the number of subsets of n vertices of size at most k is order n to the k.
Yeah, so
Now,
it is slightly difficult for me to still digest that its summation would be of the order of n raised to the power k. In fact, I just googled this thing
okay,
and found this one potential solution wherein they have given that this quantity is bounded by something which is in terms of the which is exponential 2 raised to the power n, bounded by, I mean,
no,
in
so
one of the upper bound this 2 raised to the power n term is appearing.
okay. So you are saying that it is 2 to the power n.
Yes, so my intuition says that we can verify if you give me say a vertex cover, then I can verify that whether it is forming a vertex cover or not in the polynomial time, number one.
Yes.
And since I would be considering all possible subsets of a set having n number of the elements, so that possible number of the subset would be 2 raised to the power n. And now there
Yes.
is a additional condition that the subset should be of the size at the most k. So then uh, after applying this condition, so how many subsets are there of the n number of the elements which are less than or equals to the k number of the size? So yeah, so how many subsets would be there whose size is greater than k plus 1? Yes, so this summation is bounded by this quantity, and this quantity is given like this. So they have given one Lova's bound, and even they have given a very simple bound also in one of the answer.
Mhm. I will just verify it. Maybe you are right. I'll just verify it once. So the question I should ask is, given a set of n elements, how many different subsets of size at most k can exist?
Yes, and that should be something exponential.
Exponential in
Exponential in say 2 raised to the power n kind of a thing. Could be smaller than, but
exponential in n, not
yes,
exponential in k.
yes,
Okay.
yes.
So given a set of n elements, how many different subsets of size at most k can exist?
Because the process which I tried to give
See
in
the
the
num.
answer of your question that we generate binary sequences. So in total, there would be 2 raised to the power n number of the binary sequences. And if we fix that there has to be at least k number of, or at the most k number of the ones in the sequence, but then also the quantity cannot become polynomial. It will remain exponential.
So what if k is so what if k is 2?
So if k is 2, then it shows that there would be in the assignments, there can be maximum 2 number of the ones. And those 2 number of the ones in a binary string of the length n, these 2 number of the ones can appear at how many different places? So
N choose 1 and n choose 2.
and choose 2. right?
Yes.
So therefore, this sum, yes, this is correct that we can have these many number of the subsets NC1, yeah, this thing. That at this quantity is right, NCK, but then this quantity, the sum of this quantity would be, because if we go say till k is equal to say n, we are allowed to select all the n elements maximum.
That is well understood.
Yeah,
If
but so if this k is of the order of n, if k is equal to n, then the sum is 2 raised to the power n. So if k is of the order of n, then clearly something which is exponential all of a sudden cannot become polynomial.
no, no, it is say k is of the order of n. So what this is becoming? This is becoming n to the order n. That is fine, no?
But this n is yeah, this n is actually, so yeah, this if this k is of the order of n, then
Yes.
this n has to be some constant. I mean, then this will become so very huge that it is, I mean, n raised to the power n order uh,
No,
would be,
so
I mean,
anyways, okay. So let's do it offline.
yeah, yeah,
For
sure, sure,
now, we are sure that this number, that number of subsets of size at most k, is at
yes,
least n to the power k. So omega n to the power k we can say, right? So it's a lower bound
yes, that we can say, yes,
that we can say. So yeah, so the time we are going to spend if we use this brute force algorithm is not going to be any smaller than n to the power k. That is true,
right, right, right,
right? So now we have used this kernelization trick. So instead of n vertices and m edges, now we have a very small graph. In fact, a graph where there is no dependence on n and m on the size. So you have k square plus k vertices and k square edges. So if you apply the same brute force algorithm, then the running time you will require will be n to the power k. Here n is k square, order k square to the power k. There is k to the power 2k. So even if you do the brute force algorithm, you are not spending as much time as n to the power k. You're not spending this much time. So you are spared from the dependence on n. So that is
right.
the use of kernelization. In fact, using the branching algorithm, this k in the base can become 2. So we'll have a 2 to the power k times polynomial in n algorithm. So this will use branching. So the trick is first you do kernelization. That means you apply this set of rules. You obtain a graph, which is the reduced graph, and then you do branching on this.
Yes. So what are the characteristics of, so like say vertex cover is one of those problems wherein k could be find out. So what is the characteristics of those problems for which this the dependency of n can be eliminated? Like
So
say here we can,
whenever you can find a kernel which is polynomial in k. So some polynomial in the k in sense you order k squared or order k cube. That kind of polynomial, if you can get kernel of that size, then you can eliminate the dependence on n.
so what is the size of the kernel? I mean, what's the meaning of the size of the kernel?
This is
Because
the
here
meaning.
I see that uh, is this the card? Is this the size of the kernel, or is this the cardinality of the vertices and the edges?
So if you go by the generic definition, the size of the kernel would be I dash plus k dash. So in this case, because we have the vertex cover problem, so we can say this I dash, if we replace it by summation of vertices plus summation of edges plus k dash is at most k, isn't it? So that is again order k squared. So we will say that the size of the kernel is order k squared.
Yes, yes. So does this mean that basically this kernel comprises of the different heuristics? Like,
Yes.
okay, okay. So we do have many set solvers available, freely available online. Those set solvers also take the help exploit some of the heuristics to solve the satisfiability problem. But I have not seen people using this term kernel there.
So which SAT solver you are referring to? Can you give a reference?
So there are, if I Google say any, I mean any set solver, so there would be many solvers available online. Set
Okay.
solver online, yeah. So you Google this set solver online and say this is DPLL set solver is now is so I shared its link with you. So it is this one, and then they have
Okay.
a specific way to give the input, give the boolean expression as the input. So I have pasted this in the chat, and so we give the input in the specific format, and they will let us know that what will be the assignment of the boolean literals. So I have read this thing somewhere that these SAT solvers, take the help of the some kind of the heuristics, and
Mhm.
moreover, probably in the satisfiability also there exists some limit. Uh, Before that limit, probably the Boolean expressions are maybe solvable. Don't know.
Okay. I'm taking a look at it. So what it is doing internally that we have to check. So whether it is doing some tricks as you were saying,
Yes,
could be
some
possible.
heuristics, some heuristics, some heuristics. Like say a simple heuristic would be say whenever we find say x or something y, then only one of the variables should be it is mandated to set true, and other could be anything.
So this assignment it is going to do is let us say that there is no satisfiable assignment, then it will maximize the number of clauses satisfied.
So I have only tried it to solve some of the Boolean expressions, but I did not find. Uh, but it will tell you that if the Boolean expression is not satisfiable, but then I have tried it only for the Boolean
Okay.
expressions of the limited length,
Mhm. Yeah,
simple
so of
Boolean.
course, yeah. So of course it must be doing some heuristics, otherwise it's an NP complete problem. So we can check what are the internal details. But
Yes, yes,
interestingly, the other link that you have sent, I just looked at it. So the math overflow link where the sum of the first k binomial coefficients for fixed n uh, somebody has answered.
yes,
So the accepted answer says that f of n comma k, capital N comma k, where n is, let us say in our case, the number of vertices, and k is in our case the maximum subset size that we want, is less than
yes.
equal to n choose k into n minus k minus 1 by n minus 2 k minus 1. That is again uh, is polynomial. So it will be order into the power k, right?
Uh, where is it written that?
So you look at that answer. 15 answers are there. The first answer, which has 78 upvotes, the accepted answer.
Yes. So this is less than or equals to this quantity, and this quantity is NCK thing. Okay. Okay.
So he has proved that it is actually order n to the power k, and which is not surprising because the exponents like 2 to the power n is the sum of the entire series. So now it is becoming polynomial in n to the power k only if k is constant. I mean, it's polynomial in n only if k is constant. But the
Yes.
dependence, the
Uh,
thing is the largest number in the sequence is dominating. So
ye- but if you go
it's
slightly below, then in 36 number, they have
yes.
referred to a preprint, and they have given this bound as that it is less than 2 raised to the power n minus 1, and then this thing here, n choose k plus 1 divided by n c n by 2.
Okay, that
So
is probably that is also right, but the accepted answer says that the better bound is n to the power k times something.
okay. So maybe because after making some more calculations, finally this exponential value may become some order of n raised to the power k. Maybe.
Yes, yes, yes. In fact, there are
Yes.
so many. In fact, you can look at it. I will also look at it offline, and there are so many references. So maybe the other one which the other person has suggested is a older estimate, older bound.
Okay. Yes. Yes, people have written so many things about it that that if what if the this n is k is related to n or not related to n. Yes, they have yeah, viewed it from different perspective.
Correct. Okay, so we are almost towards the end of this session. So what we have demonstrated is that with the help of kernelization, we can, considerably or not considerably, we can get an instance uh, from the original instance which has no dependence on the size of the original instance. Rather, the size of the reduced instance becomes dependent on the parameter of our uh, fixed parameter tractable algorithm. Uh, so what I planned that after this, there was this branching algorithm, which I planned that, okay, so maybe you can just look it up, that it is possible to get this running time down to 2 to the power k from k to the power k using the branching technique. So other than this, the plan was to talk about important cuts. So in this week, we have seen important cuts and the questions. So 2, 3 questions we would have taken, but
But yeah, so but then I could understand this kernelization thing pretty well. Matlab, I got the gist of what this process is. I have one small doubt here that here we could show the kernel or the two heuristics for the vertex cover problem, and if I look for some other problem, then are there guidelines available that how to find kernel or the relevant heuristics for the different problems for which there exists a fixed point tractability?
so you are saying that whether there is a template which you can use to find these reduction rules for different problems.
Yes.
So I think I'm not aware of any template. The reduction rules are always problem specific, and the reduction rules are designed so as to, you know, make sure that you can reduce the instance as much as possible. And there are results that for problems there exists problems for which we cannot design polynomial time algorithm kernels. So k to the power c kernel size is not possible. So that those kind of problems are not, you know, tackleable, handleable using kernelization.
And to which quantity you refer to this size of the kernel? I assume that just now because in the previous question you answered this the kernelity of I dash plus k dash.
Yes,
So how can this be of okay, all right, fine, now understood. Yeah, this should be of the order of k raised to the power c.
yes. K is the original parameter, so the
Ah,
parameter of the original instance.
yes. Yes.
Yes.
So why do we have, I mean, why do we have the name of this course as parameterized algorithm? Because kernelization probably just one portion of it. And so in general, I mean, why do
No,
people call this?
kernelization is only a reduction trick. And after
Huh,
that, So the kernelization is not the whole algorithm. So you have an algorithm. So the algorithm has the first part of the algorithm is the kernelization, which is also called pre-processing. So you can also call it pre-processing of the input. And then you apply, subsequently you applied something. So you have a second part. So then you obtain a total running time of 2 to the power k order n to the power c. And then we say that, okay, this problem is fixed parameter tractable for the parameter k. I mean, not k, parameter size, for the parameter which is specified for the parameter. So all the fixed parameter tractability claims are with respect to the given parameter for the given parameter. Yes. So the
Yes.
kernelization is not the whole algorithm, and therefore the course why it is called parameterized algorithm has very little to do with kernelization. Kernelization is only part of a fixed parameter tractable algorithm.
Okay. Okay.
Okay, so uh, this is the end of it. I think we were not able to discuss any questions of week 8, but it's a good exercise to sort of go through the basics. And in the next session, I'll try to accommodate some questions as well as Shivang's query on those two topics, that theorem, Poisson theorem, and that second order monadic bounds and other things. So yeah, I think we can close for today.
Yeah.
Thank you.
Thank you very much. Yeah. Thanks, Enter. This session
Okay.
was too good. Thank you very much.
All right. Thanks a lot.
Bye. Bye, everybody.